A common setup for capacitors in a circuit is like this. You'll have your input power source sent through a resistor, then through a capacitor, then back to ground. Then what you'll do is instead of taking power or signal from this source, you'll read the output of this. Now why would you want to do that? Capacitors tend to resist fast changes in voltage. So this is a way of stabilizing the output of whatever you're taking a reading from. It's called a low-pass filter because it filters out high frequencies and lets low frequencies pass through it. And I've set one of these up here. I have this frequency generator sending its signal through a 1 kilo ohm resistor and then through a 1 microfarad capacitor. And I'm taking a reading from the middle. On screen, the green trace is the actual input voltage, and the blue trace is our output voltage from our filter. Now you'll remember that an RC circuit has a time constant of RC. 1 microfarad times 1 kilo ohm is about 1 millisecond, or 1,000 hertz. So frequencies below 1,000 hertz, it lets pass just fine. And you can see on the screen, right now we're at 30 hertz, and the amplitude of both of the signals is about 1.9 volts. As I raise the frequency, though, the amplitude of our output signal diminishes. Once we get to our characteristic frequency, it's about a third of our input voltage, an E-folding. And as we go to higher and higher frequencies, the signal diminishes to 0. Now what use is this to us? Well, we can figure that out by introducing some noise into the system. Now, what if this noisy mess was our input signal? You can kind of see a shape to it, but you can't tell much of the specifics there. Look at that, there are frequencies on frequencies. But if we send this through a low-pass filter, the output becomes still a little bit noisy, but much, much cleaner. If we reverse the capacitor and the resistor, we get a high-pass filter. It's the exact opposite of a low-pass filter. It'll filter out low frequencies and let pass the high frequencies. So in this case, if we start around 140 kilohertz, our input and output signals are pretty similar. But once we're well below 1 kilohertz, our output signal starts to go to 0. Now if instead of a capacitor, we put in an inductor, we'll get the opposite behavior that we would with a capacitor. So instead of a high-pass filter, this will give us a low-pass filter. Here we are, well below the cutoff frequency. And here we are, rising above it. And vice versa when we swap the inductor and the resistor. We have a high-pass filter. Here we are at high frequency. And at lower frequencies. Now what happens if instead of a capacitor and a resistor, or an inductor and a resistor, we took the output of an inductor capacitor circuit? At extremely low frequencies, we find ourselves basically loading up the capacitor with voltage, and we're just sort of measuring that. Near the resonance frequency, we can see that our output signal is just slightly tailing our input signal. As we reach resonance, we get a higher output voltage than input voltage, and we find ourselves 90 degrees out of phase with our input. Then after passing resonance, we're 180 degrees out of phase, and the signal diminishes to 0. This is the basis for transmission lines.